In this video, we put the Solow model to the data, and the sources on which this video is based are the Handbook of Economic Growth chapter from 2005 by Durlov, Johnson and Temple, Growth Econometrics, and the textbook Economic Growth by David Weil from 2012. We've already seen in the videos on the Solow model that it can explain three stylized facts rather well from a qualitative point of view. So long-run economic growth as driven by technological progress, so that economic growth is rather similar across similar countries with a similar level of technology. That there is convergence after wars. We've seen this with Germany after the Second World War. And that in principle, the Solow model can explain cross-country income differences by differences in the parameters of the model. In this chapter, we will now look at the fit of the Solow model to the data, and we'll ask ourselves how well it fits quantitatively, not only qualitatively. And here the first question that we ask is how well the Solow model can explain cross-country income differences. And the second question, the second part, how well it explains convergence from a quantitative perspective. So what is the speed of convergence that the Solow model predicts, and what is the speed of convergence that is found in the data? So first of all, we ask ourselves how well the Solow model explains cross-country income differences. And to this end, we assume that we compare two countries that are similar in all respects except for the saving rate S, because capital accumulation, the baseline version of the Solow model, is the main explanation for medium run growth. So we ask ourselves how much of cross-country differences in terms of income can be explained by differences in investment and savings. For that purpose, we do not use labor augmenting technological progress, but we use a Cobb-Douglas production function of the form as it is stated here, where technological progress basically appears as Higgs neutral. And the reason for that is that with Higgs neutral technological progress, we can isolate better the effects that capital accumulation has on economic growth from the effects that technological progress has on economic growth, which we will look at in another video. Now, if we assume that per capita or that aggregate GDP can be explained by this production function, we know that per capita GDP is just the aggregate production function divided by the number of workers. So we get a per capita GDP of this expression here, where capital per worker is raised to the power of alpha, and the whole expression is then multiplied by the level of technology. Now, to focus on differences in the saving rate, we set the population growth rate and the rate of technological progress to 0. And therefore, we deal with the following fundamental equation that we already know from the videos of the Solow model without technological progress and without population growth, where the capital stock per worker increases with gross investment, which is the saving rate multiplied by GDP per worker. So that's gross investment. And we subtract depreciation, and the difference would be the change in the capital stock per worker. Now, if we focus on steady state differences between countries, we of course also focus on the steady state of the fundamental equation. So that is the case where the capital stock does not change anymore. So when capital per worker does not accumulate anymore, so the time derivative of capital per worker is 0. From the equation on the previous slide, we know that this is the case exactly when gross investment, the left-hand side here, is equal to depreciation. And the steady state we denoted with an asterisk. So this is the steady state capital stock. So if the steady state capital stock fulfills this equation, then capital does not accumulate anymore. The time derivative of the capital stock is equal to 0. Now what we want to do here is to isolate the steady state capital stock on one of the two sides. So we do it on the left-hand side. So we divide the right-hand side by the saving rate and the level of technology. And we get delta divided by S times A, and we bring a K star to the left-hand side. So we divide by K star, and on the left-hand side, we then have K star to the power of alpha minus 1, because we divided by the right-hand side K star. Now we want to get rid of the exponent, so we raise the whole thing to the power of 1 over alpha minus 1. So we have on the left-hand side, on the right-hand side, this expression here raised to the power of 1 over alpha minus 1, and then we just want to have the exponent as a positive expression. So the denominator in the exponent would be negative, so we multiply it by minus 1, and in exchange we exchange the numerator and the denominator here in the base, because then the two operations exactly neutralize each other. So then we have the capital stock at the steady state per worker is a function of the saving rate, of the level of technologies, the rate of depreciation, and the elasticity of output with respect to capital. And what we see here is the exponent is positive. So we see that the capital stock will increase with the saving rate and technologies, and it will decrease with the rate of depreciation. Basically, all that we have already observed in the videos on the qualitative predictions of the Solow model. Now, what does this imply for per capita GDP or per worker GDP at the steady state? Well, we know per capita GDP is given by this expression here. So we have per capita GDP as technology is multiplied by capital per worker to the power of alpha. So we just take this expression here, multiply it by A, and raise it to the power of alpha to get per capita GDP. So when we do this, we have here for this expression an alpha in the exponent, that's this one here, and the whole expression is multiplied by A, that's this A here. Now we see A appears outside of the parentheses and inside, so we put this term here outside of the parentheses, so we get A to the power of alpha divided by 1 minus alpha from here, and we can then put the two terms here together, because that's the same as A to the power of 1 minus alpha divided by 1 minus alpha, of course. So then we can just simply add up exponents here, and we get A to the power of 1 over 1 minus alpha, because this alpha and this alpha here cancel out, and we have this expression remaining here, the saving rate over the rate of depreciation to the power of alpha over 1 minus alpha. So that's now per capita GDP of a country at the steady state. Now we will look at the differences between two countries at the steady state. So we will assume that these two countries differ by the saving rates, because typically, they could differ also in the parameter alpha, delta, level of technologies, and of course the saving rate. But alpha and delta are usually rather similar across countries. So there is no reason why the rate of depreciation should be substantially higher in one country than in another. And also the output elasticity of capital is usually assumed to be rather similar. And for the sake of the experiment that we do, we also assume that technologies are the same across the two countries that we compare. So the only difference is the saving rate S. And that means, in essence, that we isolate the influence of the saving rate on the difference of per capita GDP of the two countries, as we would do it in a controlled experiment. So we leave everything else the same in the two countries, but we assume that they have a different saving rate. Well, what would the Solow model qualitatively say in this case? Yeah, it would say we compare two countries at the steady state. One has a lower saving rate, say S, and the other one has a higher saving rate, S prime. So that means, of course, that the country with the lower saving rate will have the lower capital stock at the steady state, and the country with the higher saving rate will have the higher capital stock per worker at the steady state. And as such, the country with the lower capital stock and the lower saving rate will also have the lower per capita and per worker GDP as compared to the other countries. So that's what we already know, but now we look at the quantitative effect that we get for reasonable parameter values. To do this, we now divide the income levels that we derived earlier of the two countries among each other, and assume that the two countries are similar except for the saving rate, where country 1 has a higher saving rate than country 2. Now, if we divide the GDPs, per capita GDP, then we see that many things basically drop out. So A is the same in the two countries, delta is the same, alpha is the same. So actually almost everything drops out except for the ratio of the saving rate of country 1 to the saving rate of country 2, and this to the power of alpha over 1 minus alpha. Now we said alpha, the empirically plausible value of alpha is 1/3, and we plug in this 1/3 here, and if we plug in 1/3 here, then we get 1/3 in the numerator and 1 minus 1/3, which is 2/3 in the denominator. So 1/3 over 2/3, that's basically 1/2. So we have, when we move from here, where we didn't yet plug in the values of the parameters, to here, we have 1/2 in the exponent. And with respect to the saving rate, we now assume that we compare a high-income country with a low-income country, where the saving rate in many high-income countries is about 20% gross saving rate, and in many low-income countries it's much lower, say 5%, because in this case we then have a nice numerical example. In this case, we would plug in the saving rate of the high-income country in the numerator, the saving rate of the low-income country in the denominator, and that's 0.2, the 20%, divided by 0.05. So that, of course, is 4 within parentheses. Now, to the power of 1/2, that's the same as the square root. So we have the square root of 4, and that is equal to 2. So the ratio of the per capita GDPs of the two countries that the Solow model would predict simply based on the difference in the saving rate between these two countries would be a factor of 2. So the Solow model would predict that these two countries that are similar in all respects except for the saving rates, the country with the higher saving rate would have twice the income level as the country with the lower saving rate. Now, if this were the only thing that's going on between high income and low income countries, then the model could not predict the income differences that we actually observe, because in reality the differences between the highest income countries and the lowest income countries are often by a factor of 30 and even more. So from this perspective, the Solow model does not succeed quantitatively. So the differences it can explain across countries based on differences in the saving rate, that's a rather small part of the actual differences that we observe across countries. So to summarize this, we find that the Solow model predicts qualitatively the effect we observe. So the country with the higher saving rate would be associated with a higher income, but it fails quantitatively. So the difference that we can actually explain with the Solow model is rather small. This means that capital accumulation alone can only explain a rather small part of international income differences. And if we remember the modeling cycle that we had in the first video on the purpose of economic models, we know now that we can explain a certain part of reality, but in the modeling cycle, we would have to start again and extend the model to other aspects that could also contribute to the explanation of cross-country income differences. For example, one such difference and one such extension was in the Menke, Roma, and Weil model, the consideration of human capital, so that there is not only raw labor that matters for production, but actually the education of people also matters quite a lot. And of course, there are differences in education across countries. And we will see later on in another video, when we introduce differences in education, then they can also explain a part of the income differences across countries. And then we can put the things together. We can use educational differences and differences in the saving rate to explain an already larger part of the actually observable differences across high income and low income countries. Before we move on to these aspects, however, we also want to look at the empirical plausibility of the Solow model when it comes to transitional dynamics. And here we already know that the Solow model predicts that in case of two otherwise identical countries, the one that is poorer, which has the lower capital stock, will grow faster. So that's conditional convergence. It does not predict that necessarily two countries that do not share the same steady state would converge to each other. So there is no absolute convergence in the Solow model. To illustrate this, we again look at the graph of the Solow model for two countries now, one with a lower saving rate S that has a steady state capital stock per worker of K star, and one with a higher saving rate S prime that has a steady state capital stock per worker of K prime star. Now we assume these countries start somewhere with an initial capital stock K0, the country with the lower saving rate, and with an initial capital stock of K prime 0, the country with the higher saving rate. Now, naively, if we say that there would be absolute convergence, we would be surmising that the country that starts with a lower capital stock and has a lower per capita income level, therefore, would grow faster. However, we see here that actually the country with the higher initial capital stock is still farther away from its steady state capital stock per worker K prime star. So it could very well be the case that even though the country that is associated with these red lines here, even though this country has an initially higher per capita income level, still grows faster here than the other country because it's farther away from its steady state. So therefore, we do not observe absolute convergence in the Solow model. So what the Solow model predicts is conditional convergence. How can we test for convergence empirically? Now, this has been done in the empirical convergence regressions that were rather popular in the 1980s and 1990s. And the initial idea was to regress the growth rate of a country between time 0 and time t, which would be the difference in the logarithm of per capita GDP between these two time points, on the initial level of the logarithm of per capita GDP. So in such a growth regression. That was what was done in the 1980s. Now, if we would observe convergence between countries, so here on the left-hand side we have the growth rate from time 0 to time t, so gamma y of time 0 and time t. If you observe such a convergence, we would have the situation that a country with a higher initial level of per capita GDP would grow more slowly. So actually this beta coefficient would be negative because a country with a higher y0 would have a lower growth rate on the left-hand side. Now, this, however, is a growth regression on absolute convergence, actually, as we will see later on, because it does not include any control variables. Alpha would be the constant term. That would be the average steady state growth rate without the convergence process. Beta would be the coefficient that we are interested in. And epsilon is the error term. Now, what about values for beta? So beta could be -1, then actually initial GDP drops out of the equation altogether, because if that is -1, we have minus ln y0 on the left-hand side, we have minus ln y0 on the right-hand side, so it would drop out, and actually we would have the situation that income levels at date t would be uncorrelated with initial differences at all. So then we would have actually full convergence over the time period over which we have the observations. So then there would be full convergence and the countries wouldn't differ anymore at the end point that we have here. If by contrast beta was equal to 0, then we would see the growth rate on the left-hand side would not at all depend on the income level, on the initial income level of the right-hand side. So in this case, we would have no convergence at all. And for all beta values between -1 and 0, the growth rates on the left-hand side would be negatively correlated with the initial income level, so we would observe convergence, and the rate of convergence would be directly the beta coefficient. So the speed of convergence can be directly estimated because it's in this beta coefficient. However, if we do this and we plot, for example, the per capita GDP growth rate, the average growth rate now from 1970 to 2015, so that's the growth rate over 1970 to 2015 divided by the number of years, on the logarithm on initial GDP, then what we find in this scatter plot is actually no relationship at all. So if we draw a line here that minimizes the sum of the squared residuals, then we see that the slope of this line is not even discernible from zero just by eyeballing here. And if we do a regression on that, we would find that it is insignificantly different from zero. So actually here, the beta coefficient would not be significantly different from zero, and we would have the situation of no convergence at all across these 114 countries where we have the data from the World Development Indicators database. Now, however, that would be absolute convergence. And we know that the Solow model actually does not predict absolute convergence. What does the Solow model predict instead? It predicts conditional convergence, that countries that share the same steady state or similar steady states, only among these countries we would have the situation that the country with the lower income level would grow faster. A first glimpse of whether conditional convergence is taking place can be done actually by eliminating countries that are very different from other countries. So in this figure, we only keep the EU countries that we have in the data set, plus Canada, the United States, Japan, Australia, and New Zealand. And what we then find is that the scatter plot and the regression line, they indicate that there is indeed a downward sloping relationship. So we would have a beta coefficient that is negative. If you do the regression, it's also significantly different from zero. And that means that across these rather similar countries, convergence indeed takes place. The countries that are poorer initially were associated with a higher growth rate of per capita GDP over the next 45 years in this context. The first part of this slide just summarizes what we've seen in the previous two figures. What's interesting here is that Barrow and Saleh-Martin have actually analyzed conditional convergence also at the regional level, so across the states of the United States actually, and the regions of the European Union, and also the prefectures of Japan. And what they found was that actually among these very homogeneous regions, conditional convergence also takes place. And the more similar these regions are, the tighter is actually the relationship that we get. And that's what they found out. So the idea that we can take with us from this from this preliminary empirical analysis is that we can do a cross-country analysis if we manage by some way to control for cross-country steady state differences. So what we would do is we would take the absolute growth regression that we had previously, but include all different steady state determinants between the different countries, in particular the saving rate, which the Solow model already predicted that it should have effects on the steady state values. If we do this, we get an expanded or augmented regression equation that tests then indeed for conditional convergence. So here we would again have the average or the growth rate between time 0 and time t on the left hand side. Again, if we divide it by the number of years, we get an approximation of the average growth rate. We regress it on the initial level of per capita GDP, and now we include a number of control variables that should be associated with steady state differences between the different countries. And in this case, then the coefficient beta 1 would indeed be an estimate for the rate of conditional convergence, and the coefficients beta k here would be the partial correlations between the control variables and the growth rate. So actually these coefficients would show how a certain variable would affect long run economic growth or the steady state basically between different countries. As I said, these type of regressions were rather popular in the 1980s and 1990s. where many people estimated these types of growth regressions. And what the general finding was, that is also summarized in the article that I stated previously by Durlauf and co-authors from the Handbook of Economic Growth. So the results from there were basically that initial per capita GDP is negatively related to subsequent economic growth. So we observe indeed conditional convergence, and the rate of convergence that was estimated in many different papers was in the end around 2 to 2.5% per year. So the coefficient would be minus 0.02 to minus 0.225 actually. And then there have been many different variables that were included as control variables for steady state differences. And the problem, of course, here is that we have many more potential steady state determinants than we have countries in the world. So actually, it's always a decision of the researcher how many and which of these variables to include in the regression. Typical variables that were included were schooling levels, sometimes for males and females separated. And the typical finding here is that this is positively correlated with steady state income differences and long run growth. Life expectancy, also a positive correlation. The fertility rate has a negative correlation, which would be again consistent with the prediction of the Solow model. Government consumption, negative association. The rule of law has a positive association, so that's a variable that relates to institutional quality of a country. Democracy, also a positive correlation, and democracy squared negative, so that hints towards a concave relationship between growth and democracy. So democracy would be growth promoting up to a certain level, and then would not be growth promoting anymore, and could even, the effect could turn negative. Openness of a country, so the more open a country is, the faster it typically grows. Improvements in the terms of trade also has a positive correlation. The investment ratio, the inflation rate by contrast, and corruption have a negative association with growth. Financial debt has a positive relation. Corruption is again an indicator for institutions, in this case an inverse indicator for institutions. Then the log of the population size has no consistent relationship with per capita GDP growth, and that means that no scale effect actually was found in the literature. Student test scores have a positive association. Quality of bureaucracy, again an institutional indicator, positive relation. Dummy variable for sub-Saharan Africa that's typically has a negative association, and it's often included. Distance from the equator, positive association, so the farther away countries are from the equator, and the more temperate the climates become, the faster they grow. Ethic fractionalization is negatively associated with growth. A landlocked country which has more difficulties to trade with other countries, that's also negatively associated with growth. Infrastructure proxies are typically positively related to growth. Political instability is negatively related to growth. Whether institutions are inclusive, that's positively related to growth. Black market premium, that's an estimate, that's again an indicator for an inverse indicator for institutions, negatively related to economic growth. Trust, positively related to growth. Arable land, so the more land can be used for agriculture, positive association with growth. Rainfall, typically also positive association with growth, so if there are no droughts and so on. But the variability of rainfall has a negative association with growth, of course, if the weather is less predictable to some extent. Now, however, there comes a loud warning actually, because we should always be aware that this method of these convergence regressions that were popular in the 1980s and 1990s does not allow to analyze whether a variable really causes economic growth. And there are many issues why it should not. For example, endogeneity, omitted variable bias, reverse causality. So for example, with schooling, it could very well be the case that a country grows faster and therefore could invest more in education and things like that. So this method here does not allow actually to tease out the causal effect of a certain right-hand side variable on the left-hand side variable. And in addition, which is also very troubling, that's that the potentially high number of regressors as compared to the number of countries brings with it a huge potential for p-hacking, where people might just include the variables that fit to their theory that they have in the first case, and disregard evidence as it pops up that would be against their preconceptions. So, for example, if you do these types of regressions, you will see that it is that you can come up with a certain result rather easily by tinkering around with the independent variables that you take into the regression. And of course, this has led to many p-hacking attempts, in the sense that if you torture the data long enough, it will confess at some point. So we should always be aware of the fact that it is rather easy with these types of regressions to come up with a certain desired result. But also different methods for estimation can lead to very different results, particularly in case of panel data. So here we've looked just at standard cross-country growth regressions, but what's typically done, and what was the innovation in the second half of the 1990s, was to introduce panel data growth regressions. First by fixed effects regressions, where they then found out that this is of course problematic because of the nickel bias, where the lagged dependent variables then correlated with the fixed effects and so on, and later on with system GMM estimates. But these methods often lead to very different results. So if you use, for example, system GMM or versus difference GMM estimators, it could be that the results are completely different in the end. So also different methods for estimation can lead to very different results. So potential solutions here are to get closer to the causes of economic growth, instrumental variable regressions, so that you find a variable that is actually correlated with another variable, so that you can instrument this other variable by the first variable, the instrument. But for that, the instrument should not be correlated with the outcome through any other path than the variable that you instrument it with, and furthermore, it should be a strong instrument, in the sense that the correlation with the variable that you want to instrument should be high. So these two restrictions should be fulfilled. The exclusion restriction, that there is no other pathway that is not controlled for by which the instrument affects the outcome variable, and that it is a strong instrument so that it really explains the variable that you want to instrument. Co-integration analysis was also rather popular at times, so where you find co-integrating relationships, equilibrium relationships, where you then can tease out causal effects. And of course, lately, particularly in development economics, randomized controlled trials, which are of course typically rather difficult to apply, cannot be applied at all in macroeconomic contexts. So it's typically rather from a microeconomic perspective that they have value. Then to address the issue of p-hacking, Bayesian regressions and lasso estimators have been proposed, where you actually let an algorithm decide which variables to include as control variables on the right-hand side. And of course, they have also led to important insights. For example, a paper in 2004 by Solow, Martin and co-authors, which found that many of the correlates that are typically proposed for including us on the right-hand side of these regressions are not really robust correlates with economic growth. So their sign often switches depending on which variables you include in the regression. And there are some robust correlates to economic growth, and they've described this in more detail in their paper. And Lasso is even more sophisticated algorithm to come up with the core of those variables that you should include in the end. And finally, Monte Carlo simulations have been applied to assess the quality of different estimation methods. Here, with respect to this point, that the results might also change depending on different estimation methods. And these Monte Carlo simulations have shown actually that the results can change rather dramatically if a different estimation method is used in the end. Finally, after these words of caution, we would like to know basically how well the Solow model predicts convergence as compared to the empirical estimates. Now, what can be shown is that in the vicinity of the steady state, the rate of convergence in the Solow model is approximately equal to 1 minus the output elasticity of capital multiplied by the population growth rate plus the rate of technological progress plus the rate of depreciation. Now, if we take reasonable parameter values, such as alpha 1/3, as we've already used it frequently, a population growth rate of 1%, which is close to an average population growth rate of the World Development Indicators for many countries, a growth rate of technologies or technological progress of 1% per year, and a rate of depreciation of 5%, then actually this expression tells us that the rate of convergence is 4.5%. So a country each year eliminates 4.5% of the distance to its steady state, or if you will, the poorer countries catch up with the richer ones, conditional on their steady state levels, with a rate of 4.5%. That's what the Solow model would predict. However, most empirical estimates are at the order of 2 to 2.5% per year, as I already mentioned before. So we have again the situation that we had with respect to the explanation of cross-country income differences, that the Solow model predicts qualitatively the effect, right? So it predicts a rate of convergence, but this rate of convergence that it predicts is much higher than the rate of convergence we actually find in the data. So from a quantitative perspective, the Solow model does not predict convergence right. And again, this is a reason for why we should then go back in the modeling cycle to refining the model. And as we will see later, as it was also the case with respect to cross-country income differences, if we introduce human capital and differences in education across countries, this can also lead to more consistent predictions of such a model with respect to the convergence rate that then fits better to empirical findings.